Dear friends, today we will look into the working principle of a transformer. Actually, transformer is an electrical machine, but it does not have any moving part. That is why a transformer is referred to as a static machine. Transformer is widely used in power transmission and distribution grids and industries, mainly to change the level of voltage from high to low or vice versa. A transformer has three main parts, two windings, and a metallic core, on which the windings are wound. Transformer works based on Faraday's law of electromagnetic induction. Faraday's law states that the magnitude of the EMF or voltage around a closed loop is equal to the rate of change of the magnetic flux through the area enclosed by the loop. To understand the working principle, consider the basic prototype of a transformer as shown here. As I indicated earlier, the major parts are: winding 1, where the input supply is given, we call this as primary winding. Winding 2, where the output supply is taken, we call this as secondary winding. Both primary winding and secondary winding are wound on a common core. This is made of laminated steel plates which have very low reluctance. When an alternating current is allowed to flow through the primary winding, there will be an alternating flux produced surrounding the winding. The magnitude of this flux is proportional to the magnitude of the current flowing through the winding. The secondary winding is placed in this area of alternating flux produced by primary winding. So, as per Faraday's law, an EMF is induced in the secondary winding. This is our output voltage from a transformer. Suppose there is no magnetic core is provided for the windings. Now both the windings are coupled magnetically through air. Air has relatively high reluctance. As the path of magnetic flux to the second winding from first winding is through air, it will not allow the second winding to be linked with maximum flux. In this situation, the induced EMF in the secondary winding would be quite small as because the flux linkages is small. Hence rate of change of flux linkage is also small, and as according to Faraday's law, induced EMF across a coil is directly proportional to the rate of change of flux linkage. So the amount of induced EMF in the secondary winding will be very less. In fact, only a small portion of the input power is transferred to output through the secondary winding. Now, if we want to transfer maximum electric power from primary winding to secondary winding, we have to link maximum flux of primary winding to secondary winding. This is done by placing a low reluctant magnetic core in between these windings. Steel is a well-known low reluctant magnetic material, so we would normally use steel for making low reluctant magnetic core in the transformer. As soon as we place a steel core in between these windings, nearly the entire flux which was surrounding the first winding will be concentrated inside the core and will be linked with the second winding. As nearly the same flux links with second winding, now the rate of change of flux with respect to time is equal in both windings. So again, as per Faraday's law, voltage or EMF induced per turn, in both windings will be the same. We have already explained that voltage induced across the primary winding is same as a supply voltage. Now if this primary winding has N1 number of turns, and supply voltage or induced voltage across primary winding is V1. Voltage per turn in the primary winding is V1 by N1. So far we have understood that exactly this V1 by N1 voltage will appear across each turn of second winding. So if this second winding has N2 number of turns, then total voltage across the second winding is N2 multiplied V1 the whole divided by N1. Let us say, this is V2. If now any closed circuit is connected across the second winding, it will provide voltage V2 across the circuit, and due to the voltage, there will be a current flowing through the circuit. Normally in a transformer the secondary winding is connected with load circuit. If the number of turns of secondary winding is not equal to that of primary winding, that is if N2 is not equal to N1, then secondary voltage of the transformer is different from primary voltage. Now if N2 is greater than N1, the secondary voltage will be more than primary voltage. Such a transformer is called a step-up transformer. On the other hand, if N2 is less than N1, the secondary voltage is less than the primary voltage. This is called a step-down transformer. The input power and output power of the transformer is same, neglecting losses incurred in a transformer core and windings. Power is equal to voltage into current, P is equal to V into I. Let's say, V1 is the primary voltage of a transformer. V2 is the secondary voltage. I1 is the primary current. I2 is the secondary current. Then we can write the transformer power equation as V1 I1 is equal to V2 I2. From this equation it is understood that in a step-up transformer, secondary voltage will be higher than primary voltage, and secondary current will be lesser than primary current. In a step-down transformer, secondary voltage will be lesser than primary voltage, and secondary current will be greater than primary current. All the above is explained only for single-phase transformer. Here there is a phase and neutral each at primary and secondary. In power systems we generally use three-phase transformers. In such case there will be 3 primary windings and 3 secondary windings. All windings are magnetically coupled by same magnetic core and each winding are insulated from one another. Windings at primary are connected in delta connection always. Depending on the type of transformer, the secondary windings are connected in delta connection or star connection. In delta connection there will be only 3 lines, for 3 phases. In star connections there will be 4 lines, 3 phases and 1 neutral. Till now we were discussing the elementary basics of a transformer. Hope this is useful for you. Please post your opinions below. Thank you.